at Parsons, my country. I've been there about 10 years. What I'm here to talk about today is chaos engineering for AI systems. So before I get into this, let's do a little bit of audience participation. So first up, how many of you are familiar with chaos engineering already? You know what it is? Okay, a few hands, not a ton. How many of you, and this is probably going to be fewer, have actually used chaos engineering in your programs or in your systems? Anybody? Hey, I see a couple. That's fantastic. All right. So chaos engineering for AI systems, I'll spend just a little bit of time talking about it, but first, who am I? I've already kind of introduced me, but the big reason why I can be up here talking about this today is because I break stuff on purpose, and I don't get fired for it. My boss is right over here. He can vouch for that. This is kind of the way that we do things. Of course, my image is AI generated, which is kind of the purpose of today's talk. We're talking about chaos for AI, so. All right, so here's our agenda. You can read it if you want. We're basically going to step through what chaos engineering is at a high level. We'll talk through some specific AI chaos experiments. One of the things I want to mention is chaos engineering was created to test the infrastructure of systems for their resilience and their fault tolerance in a real-world production environment. You can do infrastructure tests with AI chaos experiments as well, but that's not actually what I'm going to talk about today. What I'm talking about is experiments on the models themselves, on the systems that we use to build them, so our MLOps pipelines, all of that kind of stuff. It's a little bit different, but still based on the same principles. So moving on to that, what is chaos engineering? It is based on the scientific principles of experimentation. So there's 5 steps that go into it. First one is absolutely essential, and that's assess and understand your system. Don't run chaos on a system if you don't know how the system behaves, fundamentally, right? You gotta kind of know what it is, you have to have some visibility in place, that type of stuff before you can do it. Once you've assessed your system and decided it's good to go for chaos experimentation, you form a hypothesis, or in chaos engineering we call this an experiment. So this is what you're actually going to test. You plan out what that experiment is going to look like, what are the steps of it, who's the stakeholders, will look more at the criteria that goes into that ahead in a little bit. But you have to really well plan it. So one thing I want to emphasize here, chaos engineering can look chaotic, but it is not random. It's a very disciplined practice. Once you've planned your experiment, then you get to do the fun part, which is running the experiment. So this is that injecting a failure on purpose into your system to validate how it behaves. And then finally, you're going to monitor the system, of course, as you're running the experiment, but you're also going to look for opportunities where you've got a lot of value from the experiment and where it's worth repeating. So the idea with chaos experiments is just like any good testing, it's not a one-off run. You're going to do this, and you're going to do it multiple times on your system over time. So a little more about chaos engineering. It was originated by Netflix back in about 2008. Date is a little bit sketchy. I've seen different dates that are listed for it. But they created it when they initially moved all of their worldwide production into AWS. And they quickly realized that AWS is a different beast from an on-prem deployment. Failure happens, you have to plan for it, like Werner Vogels loves to say, failure happens all the time. So they realized that they needed to test a little bit differently than they'd been doing before. And chaos engineering came from that. One of the key components of chaos engineering, folks, is that you are running these tests in your production environment. Why did Netflix do that? If you look at the Netflix environment, it is immense. We're talking millions of nodes, we're talking locally distributed. There is no way you're going to build a test environment that's going to come anywhere close to that. So they had to do the testing in the real world environment, and that's what they built it around. But since they invented it, they actually open sourced Chaos Monkey, which was their very first experiment, back in about 2012. And many companies now around the world, Fortune 500s, Fortune 100s, across every possible industry you can think of now are using chaos experiments in their systems. It's extendable too. It started out as testing infrastructure, but there's a great book out there called, shockingly enough, Security Chaos Engineering. Strongly recommend you go check it out. That's focused on testing the security of your system using the principles and practices of chaos engineering. Excellent book, highly recommend going and reading it if you find it interesting. But it goes beyond that too. We actually at Parsons use chaos experiments to test our organizations, the people, the processes, the tools, the way that we are structured as an organization to make sure that we are efficient, effective, and resilient to unexpected absences, to business trips that get extended when we don't need them to whatever the case may be. And it's actually been a really fascinating experiment when we've run those. We've found some pretty interesting single points of failure that we didn't expect. And then finally, what we're talking about today, chaos engineering for AI systems. So as I mentioned before, chaos engineering is a disciplined approach. It's chaotic, the results can be chaotic for sure, but it is not random. It is deliberate, and you're planning it out and you're executing it carefully and with good foresight, good planning, and good support from your stakeholders. All right, so let's talk about what some of these experiments are that you can do for an AI system. There's a lot of different failure modes that you can experience in AI systems, whether you're talking classical AI, generative AI, your MLOps pipelines. There are different failure states, and they look a little bit different in some cases than what we're used to seeing, partially because AI systems are non-deterministic in a lot of ways. That's kind of the point of it, right? They do things that we as humans would struggle to do, and they use reasoning in the underground or in the background that we don't necessarily understand. So you can't test the way that you do a traditional software system because the response isn't always going to be the same. You pass the same response, the same chat message into an AI model, it's going to generate a response. Wait a day, pass the same message in again, you're going to get a related but different response. So you can't do simple checking of what does it give you, which makes it a little tricky. But let's look at some of the experiments. So if we're talking classic AI, so these are your convolutional neural networks, these are your heuristic reasoning models, these are some of those types of systems. Some failure states that you can see, and most of these are taken from an adversarial perspective, so these are attacks that people can put upon your AI system out in the wild. Weights poisoning, hidden layer injection, this is an interesting one. They come into your convolutional neural network and essentially swap out the model with one that looks just the same but has an extra layer or two built into it. It can drastically change the behavior of the system. Model corruption, slightly different variant of that. So these are all fun things that people can do to your system to get bad results out for you. Moving into the generative AI side of things, prompt poisoning. This is an interesting one, and there have been some really cool exploits and research done into this one. This is basically how do you use prompt engineering to get the system to do things that it was not designed to do that you don't want it to do, right? And it's specifically focused on that prompt side of things. So they'll use prompting tactics like one-shot or multi-shot or things like that to just kind of lead your AI down the wrong path. Response poisoning, similar kind of thing, but it's focused on the response that it's going to provide. Jailbreaking and guardrail escape. So we've talked in the media and in the world out there, there's been a lot of conversation about ethical AI and about how we protect the users of AI, especially if they don't understand what the AI is doing. How do you give them those guardrails so that they can use AI without fear? Jailbreaking and guardrail escape is an attack now that's being done against these systems to get the system to give you things back that it shouldn't, and to encourage people to do prompting that they shouldn't. And then finally, persona hijacking. This one's a really fun one, actually. There's a lot of AI applications out there. Walk around the expo floor, you'll see a whole bunch of them, right? And they all have built into their system some variant, some form of personas that they build into the responses. That way it has a consistent voice. It talks the way they want it to. It looks at things from the way that they want it to. If you get into somebody's generative AI system, and you hijack the persona, you can change how it responds, and you can make it do things in a different way than what it was intended to do. This can be very damaging for companies that are offering generative AI-backed SaaS applications. All right, and then getting into a little more general that can be applied kind of across any type of AI model that you have. Things like data poisoning, AI bill of material corruption. So these are like your model cards that you have in SageMaker for describing the model and saying what it looks like. You can go in and modify that card so it says something different than what it's supposed to. And then people will not understand what the model's actually supposed to do, and they might use it incorrectly to get some interesting results, let's say it that way. And then finally, API latency is more of a traditional chaos engineering kind of thing. What happens if we just slow the response? What happens if we slow the input? Do we see weird behaviors? And then model loading is another kind of variant of modifying model, playing with it differently, doing weird things with it. These are just a very small subset. There are a lot of potential failure modes in AI systems. I couldn't, if I wanted to talk about this today, this would be all I'd talk about, and you'd all be very, very tired of me because I'd go on for hours. So I'm not going to do that to you because that's just me. But there are a lot. The more you start diving into this and digging into it, the more fascinating it becomes because there are so many potential failure modes and attack vectors with these AI systems. All right, so anytime you're talking chaos engineering with AWS, fault injection service is kind of the go-to, right? It's a great service. If you haven't used it, if you're not familiar with it, go check it out. It's really powerful. But the scenarios in Fizz focus on applications and compute resources, classic chaos engineering. They're not really optimized or designed to interface with Bedrock or SageMaker. They don't really focus on the models themselves yet. So what are we to do? Does that mean we can't do chaos experiments on our AI models? Of course not. It wouldn't be here if we could. But that means that we get to create our own. So a la Netflix back in 2008, we're going to come up with our own experiments to test these systems. There's some specific pieces that you have to come up with within your system as you're defining the test. And you can see those under design tests there. But you design the test, you run the initial experiments manually. Don't worry about automating them for the first couple, 5-10 times that you run the experiment. And then once you've validated the system, that's when you look at automating it and actually building it out so it's repeatable in an automated, trackable fashion. So what do we need for our design and test? I mentioned that I talked about this a little more earlier. First thing is the targeted element. This is what you're going to put under experiment. So this would be the model that you're targeting. This would be that specific guardrail that you want to attack. Whatever it might look like, that's what this is going to be. You have to define your stakeholders. Remember, folks, we're doing this in production systems, which means there can be ripple effects that are unanticipated that will be noticed by your users, that will be noticed by your stakeholders. So you need to identify who those people are and make sure that they're on board. This is how I do this and don't get fired, right? I don't just go and kick a cord and unplug something somewhere and expect to keep my job. Personnel support. These are the people that have to support the system and restore it back to nominal behavior after the test has been completed. Duration and date. Important thing to know with the duration and date of your experiment. Because you're running this in production, and because you want to see how it reacts in a real-world environment, you want to run these tests during your regular business hours, when the system is under load, and when your staff is on hand to support, protect, and recover. That's really important. Guardrails. These are the definitions that bound your experiments. So what are we testing within? What are we not going to go outside of? Stop triggers. I mentioned ripple effects earlier. Sometimes experiments go a little cattywampus. Sometimes they behave in ways you don't expect. Sometimes they cause breakage downstream that you weren't looking to see. What are your stop triggers? What do you see in your system that's going to cause you to pull the plug on the experiment and roll things back into the other? Really important things to do that before you do it. Word from experience, you will miss some of the stop triggers that you're going to wish you hadn't missed. So expect that, but it's important to try to refine them ahead of time. And then finally, your recovery plan. How do you get your system back to nominal after you've done this experiment? And what is your test plan? Right? Defining it out well. Remember I mentioned, chaos engineering can look chaotic, but it's not random. It's well planned and it's disciplined. So define your test plan. And as I mentioned before, start with a manual test. Once you've proven the value of it, once you've proven that it's something you're going to want to run multiple times, that's when you look at automating it. All right, so here's an example of a manual test that has been defined for one of our systems in the Parsons environment. The targeted element is a fine-tuned NOVA model, and the attack vector that we're going to be experimenting with is prompt poisoning. So we're going to be sending in some prompts to try to get the system to do things that it's not designed to do, that it's supposed to be prevented from doing. All Our stakeholders, because it is a corporate enterprise level system, our Parsons CTO is going to have to be informed and aware that this is happening before it happens. Security and compliance need to know, because if your system behaves weirdly and they see weird things coming up in the logs, they need to understand that that's on purpose, and that you have a plan to recover. Business unit CTOs, when it's an enterprise thing, our company is divided into business units, those CTOs should be aware of it as well, because there could be impact on their staff. Personnel support, our LLM team, the folks responsible for the model, for maintaining and managing it. And of course, my group, the Cloud Center of Excellence, needs to be involved in it because we're talking about something deployed in AWS. Duration and bait, so remember I mentioned we run these in the middle of the day, under load, when people are around. So the date that I have on here is just a sample, but 1 hour long, right at noon, so people are eating lunch, they're coming back from lunch, they're having fun. And May 21st, which is a Wednesday. So middle of the week when you have the most likelihood of people actually being there, you're not doing this in the shadows, you're doing this in public, you're doing it when you have to support. All right, moving on, guardrails. So remember I talked about those boundaries that we impose upon the people doing the test. The guardrails for this one, we're not using proprietary or sensitive data. And we're not trying to get the LLM to give us proprietary or sensitive data. Seems like simple guardrails, but that gives us some security, some confidence that we're not exposing something we really don't intend to expose in these experiments. And what are the stop triggers? So I kept these very, very general. We had actual specific stop triggers that we identified, but if the NOVA responds to prompts in a certain way, as an example, if it starts spewing racist remarks or something like that, we're going to stop doing the testing because that's a fail. We didn't do what it was supposed to. Non-involved users report unexpected responses. So if we start seeing impact out in the broader community beyond what we expected, beyond the group that we would be involved, that's something that gets us to stop and say, okay, we've done enough testing now, let's get it back to normal. And then our recovery plan, we have automated pipelines. I mentioned MLOps, so we're going to use our automated pipeline to send the old model, the same model itself, back in again to restore back the previous. And our lead time to return is expected to be well under an hour. The pipeline takes about 5 minutes to run at most, so I said under an hour is really like 5 minutes. And then the test steps. Again, I kept this super general because I didn't want to put anything out there that I would get in trouble for. So prompt the NOVA model with the following prompts. And we actually had about 15 prompts that we run through to test the system to make sure it's behaving the way it should. Document the responses to the prompts. So what does it give us back? And of course, non-deterministic, these responses are going to be a little different each time you run the test, but they should be similar. And then assess your responses against the prohibited responses. This is the one, by the way, that gets really interesting when you start automating. Because how do you assess something that doesn't respond the same every time? It gets kind of fun. There's some cool math involved in that. All right, so bottom line, as I'm walking through this experiment, it's pretty simple. There's not a lot of complexity there, right? It's clear, it's well-defined, it's testing one thing. Keep your experiments simple and focused. All right, so resources that we build with. This is now, we've run it several times. We're going to start actually automating this and building it out so we can run it multiple times over and over again. So what are we using? We use step functions for the orchestration. We use Amazon Lambda functions multiple times throughout this, but to actually kick off the test, to record the results of the test, to document the report afterwards, those are all Lambda functions, and to assess the test. And that was actually the most complicated Lambda function of that whole set, was doing the assessment. Amazon DynamoDB, we store the results from the prompts and the exact prompts that we used in DynamoDB, so it's easy to query and pull out again later. And we use the Lambda function, like I said, for the assessment of the performance, and then an S3 bucket to store those assessment results over time. So we can go back and look at the history of the experiments and make sure that they're, that we're paying attention, that we're not seeing degradation in the models we upgraded or updated, that type of thing. And then the system under test, as I mentioned, is a fine-tuning of the model. So this is kind of what the workflow looks like. We have our orchestrator up top, step functions. It's going to start by calling the test. And the test is this lovely one here, really long names. Experiment, run the prompt test. We're going to send the prompts to the LLM model. We're going to store the prompt and response pairs, and then that lambda function returns when the test is complete. This whole test really doesn't take very long, maybe 15 prompts. We keep the prompts relatively targeted and simple themselves too, so your model doesn't have to think very hard to respond. It doesn't take a lot of time. That's kind of nice. Once you get the response back from the orchestrator, then it triggers the next step. It calls the test assessment. And as I mentioned, this is the one that gets really interesting. And this one is the assess input prompt results lambda function. It goes and gets to the database to query the prompt and response pairs. It does its assessment and stores the results back in the S3 bucket, or I should say back into the S3 bucket, and then it returns its assessment of whether the test passed or failed. Now, for the sake of our testing, if the system behaved the way it was supposed to, that's a pass. If we see unexpected behavior from the system, that's a fail. We want to be explicit about that. So as I mentioned, automate one experiment at a time. The nice thing with using step functions like this is you can tie them into step workflows, step function workflows, and you can have multiple different experiments that are tied in. You'll see that on the next slide. But doing one at a time helps you get clarity on the behavior of the system with that single test. Now, as you mature this and as you build out the testing and get more and more in place, you can start chaining them together, or not chaining. In this case, we're running them in parallel. But you can see we've got 4 separate experiments in this work stream now that we've implemented and that we run. We added in a randomizer at the top of it, so we never quite know when we run the experiment what of those experiments are actually going to run. It might be one of them, it might be all 4 of them, it might be some weird combination. And that's deliberate because it lets us see what the system looks like under multiple perturbations. But we also have each of these step function implementations as their own discrete implementations, so you can run any one of them at will whenever you want to. So you can still see what the individual results are, and you can see the combined results. We added that step function, or the lambda function at the bottom to build the results document, and then one again to notify people and update the dashboards and all the fun stuff so that people can look and see the results of these experiments. All right, this is the lambda function that generates the random decision for whether we're going to run a function or not. So I apologize, that's kind of the most trivial of the functions that we use, but it's also the only one that we put on the slide and be readable, so that's why it's up here. And then these are some of the experiments that we've implemented that you can run in this system. Adding the experiments over time, right? You're going to build the complexity of your system over time as you get more mature in the practice. And this is kind of the process. So, silly little LLM generated model or image of me thinking about an elephant. How do I eat the elephant? It's not by trying to eat the whole thing all at once. It's by taking those little single bites. Start simple, start manual, automate one experiment at a time, automate more and more over time, and you're creating a more resilient, more trustworthy, more known and understood AI system like this. All right, that's all that I had. So, questions, concerns, comments, or is it? It really depends on the nature of the test. So the question for folks that couldn't hear it is, how long does the test cycle last? We have some of the experiments like the prompt one that I kind of walked through that take a minute, a couple of minutes, right, depending on the response of the LLM. We have other ones where we're testing